Now we are going to give a small lecture in some topics in digital logics. This lecture is given by Manvit and Mandeep, and a heartfelt thanks for Kannadasan sir for giving this assignment.
First we go with number conversions. Number conversion means from one system to another system. We deal with some examples here. First example is convert 634. It is in octal system. We convert to binary. First we write the decimal values from 0 to 7, where the corresponding decimal value in binary is 000, 001, 010, 011 and so on. The question is 634 in octal. We have to convert it into binary. Here 6, the value of binary for 6 is 110, and for value of 3 is 011. The value of 4 is 100. So we represent it as 110, 011, 100 to the base 2. So we convert the octal into the binary. Next, here we go with convert 3FD it is in hexadecimal. Hexadecimal means it is the base to 16. We have to convert to binary, means to the base 2. Here are the decimals from 0 to 15, where the corresponding binary number of each decimal is 000, 0001 for 1, 0010 for 2, 0011 for 3, and so on till 15. Here from 10 to 15 we represent 10 as A, 11 as B, 12 as C, 13 as D, and 14 as E, and 15 as F. Here the question is 3FD in hexadecimal. So the corresponding binary number of 3 is 0011, and for F is, here we go, 1111, and for D is 1101. So the binary value is 0011, 1111, 1101. We have to combine these binary numbers. Here is the next example. 589.B4. It is in hexadecimal, means to the base 16, to binary value. So it means we have to convert into base 2. So already we know the binary value of this for 589 and discussed in the above box. So what is the 50101, or we can represent it as BCD number 8421, and A is 1010, and for 9 is 1001, and for B is 1011, and for 4 is 0100. So we have to combine it. So the answer is 0101, 1010, 1001, 1011. Here I have to put the point, and 0100. Next example is we have to convert 25B. It is in hexadecimal, to convert to octal. Here it is to convert to octal. To convert an hexadecimal equivalent to octal equivalent, we should first convert the hexadecimal to binary, and from binary to octal. Where we know hexadecimal of 2, where we know the binary value of 2 is 0010, and for 5 is 0101, and for B is, here it is written as B, and for B is 1011. We have discussed in the previous box. Now we have to combine this 0010, 0101 and 1011 to the base 2, means binary. Now binary to, now we have to, after converting to binary, now we have to convert it to octal. So while converting to octal, we have to take 3 bits from left to right. So I took 011. Here is the 3 bits, and next one is 011. Next one is, it means we have to take 3 bits as one set, 001, and next one is 001. So what is 011? It means the corresponding decimal number is the corresponding decimal number mistake is there. The corresponding decimal value of 011 is 3, and the corresponding value of 011 is again 3, whereas 001 is 1, whereas 001 is 1. Here these are the decimal numbers for the corresponding above binary values, where we have taken 3 bits as one set from left to right. So we convert 25BH in hexadecimal. In hexadecimal we have to convert to octal, so the corresponding octal value is 1133 to the base 8. It is in octal. Now next example is 475.25 to the base 8 to its decimal equivalent. To convert AB.CD to decimal, we take like this: A into 8 power of 1, B into 8 power of 0, point C into 8 power of minus 1, D into 8 power of, so A into 8 power of 1 plus B into 8 power of 0, point C into 8 power of minus 1 plus D into 8 power of minus 2. Now the value of 475.25 to convert to octal, we have 5 into 8 power of 0, 7 into 8 power of 1, and 4 into 8 power of 2, point 2 into 8 power of minus 1 plus 5 into 8 power of minus 2. Now we simplify the value as this one is 256, this one is 56, and this one is 1. Point here we simplify as 0.328. So the final answer is by adding this 317.328 to the base 10. This one is the answer for a corresponding octal. Now next one is 3509 to convert into hexadecimal, means it to the base 16, where it is in decimal. We have hexadecimal means to the base 16. So to convert this we have to do LCM, least common divisor, with 16. So for 3509 we're doing LCM, we get 219, remainder 5, and for 219 we take 16 divisible, so 13, and the remainder is 11. Now we go from down to up, so 13, 11, 5, but we have already discussed the corresponding value of 13 is D, and the corresponding value of 11 is B, and the corresponding value of 5 is 5 only. So in hexadecimal equivalent, D, B, 5 to the base 16. So next, here we deal with the fractional values, some examples. So we have 0.8125, it is in decimal. To convert to binary, so binary means to the base 2, so we multiply into 2, 0.8125 into 2, here 1.625, where we take the first digit here written as 1. Next one we take the only fractional part, so we 0.625 into 2 equal to 1.25. Again we take 1 keep here, and we take 0.25 into 2, where we get 0.5, so 0 will be written is here, and next one 0.5 into 2 equal to 1, so 1. So there in LCM we took from we go from down to up, where but here we go from top to down, so 1101. So the final answer is 0.11101 to the base 2. Next here 0.64022625, it is in decimal equivalent. To convert to octal, octal means to the base 8. So we multiply the given decimal into 8. So 0.640625 into 8 equal to 5.125, where we keep 5 here, and we have to multiply this part 0.125 into 8, 1, 5, 1. We stop here till 1. 0.64625, it is in decimal equivalent. To convert to octal, the answer is from top to down you have to take. So 0.51 to the base 8. Next we go through hexadecimal. 0.1289062, it is in decimal. To convert to hexadecimal, hexadecimal means to the base 16. So we have to multiply that decimal equivalent into 16. So 0.128960 into 16 equal to 2.0624992, where we keep 2 here, whereas again multiply this part into 16, 0.06249992 into 16, 6249992 into 16, 0.9999872, where we take here that part 0. Next 0.999872 into 16, we gave 15, 997952, where we take 15 here, and we know in 15 means the corresponding is F, we have discussed previously, and 0.9997952 into 16, here it is 16, 2.021423. So it will be repeating. I took only from 2 to 2, and it will be the values will be more. So 0.1289062, it is in decimal. You have to convert to octadecimal. The corresponding octadecimal is 0.20f, and 20 the values will be repeating. So I took 0f and so on to the base 16. Next we go here with example 35.45. It is in decimal. To convert to octal, so we have to take LCM of 35 with 8, least common divisor, and 35 we have divided with 8, it will be 4 and remainder will be 3. 8 4 32, remainder will be 3. Next, where this fractional part we have to take 0.45. 0.45 we have to multiply with 8, 3.6. This problem will be discussed previously, where we have took 3 here, and next there 0.6 0.6 into 8, 1.8, 1, and 0.8 into 8, 6.4, 6, 0.4 into 8. So the values will be going on repeating. So I took till 3. So the answer is 4, 3, and we go from top to bottom here, 3 1 6 3 1 6, and so on.
Digital logics, we have 3 types of flip-flops. One is SR, one is JK, and next is T flip-flop. First, now I am going to tell you how to convert SR flip-flop into JK flip-flop. J and K will be given as the external inputs to S and R. As shown in the logic diagram, here S and R will be the outputs of the combination circuit. The truth tables for the flip-flop conversion are given here. The present state is represented as QP, and the QP plus 1 is the next state to be obtained when J and K are given as the inputs. For 2 inputs J and K, there will be 8 possible combinations. For each combination of J and K and QP and QP, the corresponding QP plus 1 states are found. QP plus 1 just suggests that the future values obtained from the in the JK flip-flop after the value of the QP. The table is then completed by writing all the values of SR required to get each QP plus 1 from the corresponding QP. That is, the values of S and R that are required to change the state of the flip-flop from QP to QP plus 1 state are written here. This is the logic diagram for conversion of the JK to SR flip-flop. Here the inputs we wrote as like JK, and the outputs are S and R. So from this logic diagram we are going to draw the K maps here. So we write all these values into the K map. This is 0 1, we fill like this, see S. So S is equal to 0 1 2 3 4 5 6 7. This is the notation for the K map. So we write 0 position is 0, X is in 1 position, 0, like we complete the table like this, and next we also write complete the table for the R flip-flop. So from there we take the common values like this, and we write the from the K map we write the obtained values. So next I am going to tell you how to convert JK flip-flop into T flip-flop. Here J and K are the actual inputs of the flip-flop, and T is taken as the external input for the conversion. Four combinations are produced with T and QP. J and K are expressed in the terms of T and QP. The conversion tables, here are the conversion tables, and this is a conversion table, and these are the K maps for the conversion table, and this is the logic diagram. See, we get here the JK as the actual inputs, and the T as the external input, and QP we get the products like thing. So we draw the K map from the given logic table. So from there we obtain some two values.
Start.
Now I have told you how to convert from JK to T and SR to D flip-flops. Now I am going to tell you the state diagram and the characteristic equations for T, JK and D flip-flops. So first I am going to tell you the diagram for the D flip-flop. This is the diagram for the D flip-flop. Here the input is D, and this is the clock we have put for the flip-flop, and this is the characteristic table for the D flip-flop, and from this we obtain the characteristic equation, that is Q of next. Q of next is equal to D. For the T flip-flop, the state diagram is this, and we attach a clock for this. The characteristic table for the T flip-flop is is first we take 0 and 1 as the input, so we get Q and Q dash as the Q next. From this, Q next is equal to T Q dash plus T dash Q. This is the characteristic equation, final characteristic equation. For the J and K flip-flop, the diagram is this, and this is the characteristic table. Here we have four input values, so that we get the 4 output values. From this we get the characteristic equation. Q of next is equal to J of Q plus K dash of Q. This we get by drawing the K maps. So now for this I am going to tell you the state diagrams. See, for the D flip-flop, this is one input, and it goes to 1. And if we give 0 as the input, it goes to this state, and if again we give 1, it goes again, it comes to the this state. This is D flip-flop state diagram, and similarly we can see here T flip-flop state diagram and JK flip-flop state diagram. Now I am going to tell you about the encoders and the decoders. Decoder. What is a decoder? It's a circuit which converts the digital signal into the logic signal. Its inputs will be given in the digital form, where the outputs will be given in the continuous wave or the analog wave. See, here we took the inputs A0, A1 and A2 are the inputs, and we connect it to a decoder. We get 0, O0, O1, O2, O3, O4, O5, O6, O7 as the analog signal outputs. Encoder. What is an encoder? It's an electronic device which is used to convert an analog signal to a digital signal. It is like as a BCD code. It has a number of the input signals, but only one output. Like, see here we can see 8 input symbols, and see how 0, 0, 0, 0, O0, O1 and O2 are the outputs. So this is exactly opposite to the decoder. And now I am going to tell you about the multiplexer and demultiplexer, a brief one. Multiplexer means many to one. A multiplexer is a circuit used to select and route any one of the several input signals to the signal output. Whereas we come to a demultiplexer, it is exactly opposite to the multiplexer. Here we have a single input and we get multiple outputs. So here we can see this is the diagram for the multiplexer, and this is for the demultiplexer. See, here you can see the number of the input lines are more, and we get only one output. And when we come for the demultiplexer, the input line is 1, and here 4 output lines we get. So this is the difference between multiplexer and demultiplexer. Previously I just told you what is like multiplexer and demultiplexer. I didn't tell you in detail, I just told you in brief. Now I am going to tell you what is logic synthesis. Logic synthesis is a process by which an abstract form of the desired circuit behavior, typically at the register transfer level, is turned into a design implementation in terms of logic gates, typically by a computer program called as a synthesis tool. It is a process of converting high-level description of the design into an optimized gate level representation. like we take some A, B, C, D, some plus B, D, E, F something, and conversion of that into the gate levels like AND, using AND and OR, that is called as logic synthesis. So the whole conversion we call it as logic synthesis. Now coming to binary counter. Now I'm going to tell you only the definition of the binary counter. What is a binary counter? A digital circuit which has a clock input. So we already discussed, we give for the flip-flops we give the clock as the input and a number of the count outputs which give the number of the clock cycles. The output may change either on rising or falling clock edges. The circuit may also have a reset input which sets all the outputs to 0 when asserted. The counter may be synchronous or a ripple counter. So next I am going to tell you what is a race condition. A race condition is the behavior of an electronic software or other systems where the output is dependent on the sequence or the timing of other uncontrollable events. Race conditions can occur in electronic systems, especially logic circuits and multi-thread or so we have discussed only the basic concepts in the digital logics. So we thank you for listening to our lecture, and this lecture is given by me, Manvit, and my friend Manadip. And a heartful thanks for the Kannadasan sir who has given us this opportunity to do this assignment. Thank you, sir.